The year was 1956. That year, the U.S. Navy was directed to develop a defense system that would be a strategic deterrent to nuclear aggression. A system that could fire an intercontinental missile from a submerged submarine. Back then, many thought the idea was impossible. Under the leadership of Admiral William F. Rayburn, intensive research and development was undertaken to find the most effective way to accomplish this directive. What began was a Navy contractor team effort. Enormous difficulties were overcome in those early days. Enthused by the challenge, contractors and suppliers often worked round the clock to solve problems never before encountered. A precision inertial navigational system for the submarine was developed, which could identify the exact location of the submarine without reference to outside sources. Special solid rocket fuels were created and tested, and a system for launching missiles from underwater tubes was developed and perfected. Precision systems for targeting and firing the missiles were created, which incorporated punch cards, a very advanced concept at the time. Finally, after 5 years of intensive work and collaboration between the contractors, suppliers, and the Navy, coupled with thousands of disappointments and breakthroughs, our first nuclear-powered submarine, the USS George Washington, was commissioned for patrol in November of 1960. Admiral Rayburn's team had completed its assignment an incredible 5 years ahead of schedule, initiating what was to become the most successful weapon system development program in U.S. history. Tribes and nations that could not resolve their conflicts peacefully began to turn to weapons for final solutions. Soon, bronze, brass, and iron came into widespread use, and hand weaponry and armor became even more sophisticated and accessible. As weaponry developed, walled fortifications began to be established as an effective means of defense. Nations relied on them to protect their families and provide a haven from attacking invaders. As fortifications improved, warring nations created new weapons of offense to counter these improvements. The giant crossbow, the battering ram, and improved missile launchers like the catapult became the preferred offensive weapons. During the Middle Ages, weaponry development stagnated, but was revitalized again during the Crusades. Two new weapons, the hand crossbow and the English longbow, revolutionized methods of field warfare. Defensively, armor and armored horsemen continued to improve. Skilled metalsmiths constantly devised new armor to protect each soldier. Hand weaponry was approaching its zenith. Central to the FBM system is the Trident II D5 missile. When the D5 was being developed, it had its share of challenges. When this missile was tested, all its systems didn't quite work in unison and created this visually memorable launch. Corrective measures were taken, and after 3 more test firings to verify the corrections, the D5 was given a clean bill of health. The D5 is a 3-stage missile, and as you can see, about half of the missile's length is dedicated to its first stage motor. The second and third stages were added to extend the range of the missile. In the third stage, the engine is surrounded by re-entry vehicles and contains the guidance system, the brain of this giant machine. And somewhat like a human brain, it's composed of 2 sections. The first section contains electronics for data processing. It's called the Electronics Assembly, or EA. The second section houses the measurement, alignment, and tracking assemblies. It's called the Inertial Measurement Unit, or IMU. The IMU also contains 3 groups of electronics. They are the Stable Member Electronics, SME, the Gimbal-Mounted Electronics, GME, and the Case-Mounted Electronics, CME. Collectively, they are called the IMUE, for IMU Electronics. Like a human brain, the 2 halves of the guidance system are linked together through a large multi-conductor cable carrying communications between them. They're used in the Inertial Measurement Unit, or IMU, that measurement and tracking part of the brain. From the outside, the IMU looks rather like a probe employed in underwater exploration. However, in this IMU, that porthole is actually a window that pops open for a star tracking camera. Inside exists one of the most complex electromechanical systems ever conceived. It contains a sophisticated gyro-based system that constantly maintains a stable platform to help keep the missile on target. Around this unit, called the stable member, are 3 spherical shells, all mounted on gimbals, which enable the unit to serve as a reference point regardless of the missile's attitude. The entire unit's interior environment is completely sealed and controlled to withstand the extremes of space. As you might imagine, it takes thousands of complex, critical tolerance parts to create this incredible apparatus. And each part created for the IMU is assembled with utmost care in the cleanest environment possible. In the end, all those uniquely designed gyros, bearings, sensors, mirrors, regulators, connectors, seals, and hundreds of other additional parts combine to make the IMU one of the most sophisticated and complex guidance systems ever designed.